that yeah, so this is not one of those classes where we will be doing some new topic um, which is there in the syllabus or something. So so we can do it in two ways. Either so you guys can ask me questions on whatever things has been done if you have any doubts, or as somebody last time requested me to kind of do a little bit of Fibonacci heap and how its applications in the area of Dijkstra's algorithm and so on. I can try to explain that. But any questions, anything, any doubts? I'll be happy.
Hello, sir.
Yeah.
The practice problem set of dynamic programming. The first question was, can you open the first question? I mean, I was trying it, but if you finding it difficult to form the difference.
Oh, the dynamic programming practice problem, right?
Yes, sir.
Okay. Yeah, okay. Yeah. Hello.
Yes, sir.
Yeah, so what was the question?
I mean,
What is the question?
hello.
Well, I think your connection is not. Yeah, somehow I'm not able to hear your connection. Your question.
Hello.
Yeah.
Yes. I
Yeah,
mean,
hello.
the question was, suppose we have infinite supply of each of S equals to, I mean, S1 is to SM valued coins. I mean, there are coins S1 to SM, and we have infinite supply of those coins. Now we have to design an efficient algorithm such that given an integer capital M counts the number of days in which we can generate in rupees with S1 to SM coins.
Right. Right.
But I'm finding it difficult to form the difference.
Yes. Finally, required to form recurrence.
Yes, actually I'm doing it, but later I realized that I'm doing a lot of overcounting.
So there is a chance of overcounting that can happen. One thing that you can do is, of course, what is the thing that you want? What is the component that you are counting actually? What is the recurrence on that you are doing?
I mean, for the values, I mean, we have to find the number of days for to generate capital N rupees. So I'm starting from 0, 1 to up to N. And how many ways we can? Capital N.
N.
Yeah.
Capital N or
capital N. Capital N rupees.
Capital. Yeah. So it's a dynamic programming, right? So ideally,
Yes.
you should be thinking. So consider this Cij.
Yes.
Is the say something like Cij is the number of ways of generating I rupees using S1 to Sj.
Okay.
Okay. And try to write a recurrence for this.
Oh. Acha. Yes. Right.
Yeah, try to write a recurrence for this, and then you will be able to do it.
Okay, sir.
Yeah. Okay. Any other questions? So, by the way, just one quick thing. I mean, how many of you are here from the MTech CS? I think at least I think Luna is there, right? Udalok is there. So did the were you consulted when the timing for the NSM was chosen?
Temporarily we fixed a date. I mean, we had a consultation with CRS also, and
Okay.
Yeah.
Right, because I mean, I got a information from the CRS people about time. That time was I think okay, I'll tell you what. On the 27th, if I'm not wrong. Yes. It's 27th July. So I mean, so where do you guys consult? If it was consulted, then I have no problem with that. Hello.
Yeah. We consulted, and it is 27 from our side also, I think.
Okay, perfect. Very good. And what about the the JRFs? Like Swarnalipa or
Sir, actually, we also have decided on 27th only.
Okay.
Yeah.
27th. Okay, that's fine. I mean, I'm perfectly fine with 27th. I'm just wondering that it should not decide not on the same page. And then it will. Okay. Fine. So good. So if 27 has this. Excellent. Hello. Is there a problem with my connection today?
Yes, sir. Sometimes
Yeah.
not able to hear, but now it's fine.
Okay. Oh, it's fine. Yeah, I'm not usual place, so that might be a problem. It's okay. Yeah. So, any other questions before I can maybe go into this talking about Fibonacci hips? Yeah. Okay. So, if not, let me start directly into this Fibonacci hip thing. And again, I must repeat here that whatever I'm going to do now, that is not a part of your syllabus. Okay, I mean, this is not going to, I'm not going to ask you questions based on them, that it is a very important concept, and so that's why we are trying to talk about it, because you guys were interested in it. So what we are trying to talk about is Fibonacci hips in Dijkstra's. Now, okay, so let me quickly recall what was Dijkstra's. Okay, so what was Dijkstra? So if you guys remember, so it was basically finding out the single source shortest path, right? Single source shortest path algorithm. And what it did was that it always, it kind of, it has this graph G, and at any point of time, so this G was a V comma E. At any point of time, it had a set of W, which is a subset of V. So there's the S, and there's this set. And these are the things for which we already know the shortest distance from S, right? So we already know the shortest distance for S, from S to all the vertices in W. And our job is constantly increasing the size of W. And the main idea was that you take any other point, right? Any other point, any other vertex. So for all vertex, so for all W in W, okay, we know, say D of W, the shortest path length from S to W, right? And for all V not in W, right? What do we know? We also know the current shortest path. Okay, we have D of V. This is the shortest path from S to V using vertices in W. So look at any path that goes from here and just right from the boundary, it goes makes a direct jump. So you know this, that is the amount that is stored there, right? And the main algorithm is nothing but the algorithm is basically at any point of time, at every round, pick a V from basically W with the minimum dV, right? Add V to W, right? To update D of say V prime for all V prime in V minus W, right? And so on. And you keep on doing it. So this is basically the algorithm. Do you guys recollect this one?
Yes.
Yeah. Good. So if you okay, so now what is the time complexity of this? Now the time complexity, of course, finding the minimum is not the hard part, right? Finding the minimum is not the hard part, because in some sense you can always almost maintain the minimum. You can maintain the minimum that is there or something. You can store these things in a heap and so on and so forth, right? So you do this whole process, you do it, this round is done size of V times, right? This whole thing is the size of V times. Now this step, pick a minimum, right? How much time does this take? Now, if you use heaps and all, this takes order of log V times, right? So that's not a big deal. Okay. But the problem is this, actually, it's okay. So sorry. Okay, let me come back to this. I mean, this is not. So what we have to do is just two things, right? We have to pick a V in this, right? And not only that, we have to update this all the V's. Okay. These are the two things that we have to keep on doing it. Okay, so I just kind of jumped myself. So picking a V, maintaining the minimum value of V is not easy, right? So this can be done easily in order V steps. It's picking up the minimum. So that's the very standard one. So we have to do two things. Okay, we need two things to do two things. Number one is pick a minimum. And number two, update. Now, before so how many times we have to update? Can somebody say how many times you have to update it? Hello? Anybody? How many times you have to update it overall? How many updates have
V will
sorry?
No, sorry.
No, go ahead. Whatever it is, don't worry. Just tell me something.
Yeah. Just V will.
So for every time, of course, you can do V of them, right? So that is a very standard upper bound. So in that case, you do a V updates and it becomes V square kind of stuff. So whole thing is like, okay, you take order V. So one way of thinking of it is that you have order V over here and order V over here and V over here. So every round you take V plus V. So the simple analysis is order v square. Right? Every time you take this one, you update it, you find out some one. Right? Now we can do slightly better. Okay. Why? Let's look at all the total updates. Let's take this total updates out. Okay. I will kind of think of them, that all the possible updates that you do in the whole graph algorithm. Right. So note that in this graph, right, if at any point of time, say this vertex has just been added. Okay, this is a vertex that has just been added, or maybe I'm letting it in a different way. So this vertex has just been added. So that means now my new W has become this, right? Then which all V does it change? The dV will change for which all V, right? So if this is changed, if I have no path, okay, no direct edge from here to here, do you think this d of this vertex, say this is say V2, will this change? Do you think it will change?
No, no.
It will not, right? Because you want the shortest path from S to this vertex, from this vertex to this vertex, just using the vertices of W. And now all that I have got, I've already stored it. Now all that I've got is one extra power that we have got, is that I can use W, right? That's it. Right? I can use V, sorry, I can use V. So maybe, and note that there's another important thing here. Okay, so note that all the other vertices actually have length actually less than W. Okay, so this is something that you can see, that all the other vertices that are there here, the distance of that vertex from S is lower than the distance of S from V. So if at all this quantity has to be changed, it must be that there is a path that uses V and then directly jumps to the that vertex V2. So if a vertex V2 is a distance, is not a neighbor of this green vertex, I don't need to update it, because that edge does not change. That the smallest path from S to V2 using vertices of W does not change. So only thing that changes are therefore this set of all neighbors of these new vertices. They might change. Okay. They might be the ones that change. So basically, every time a vertex come in, I might have to update its degree number of points, right? So total number of updates. So total updates. So total updates. Now this is I'm not saying that update per round. Okay, total updates. Therefore, nothing but summation of BI, which is 2 times E. Right? Aha. Is it clear, this one? So yeah, so the time complexity, therefore, so time complexity is what? So the time complexity becomes, okay, so there are V times I do this one, I have to do this minimum. So I can say that this is V times the time for finding a minimum plus number of updates times time for updating. Okay, so think of it this way. So this is what I have managed to produce here. The Reich's algorithm gives. Okay, it says that the time complexity is this: size of V times the time for finding a minimum among all the set of vertices that are there, among all the set of stuffs, plus the size of the edge set times the time for updating. And now here is the data structure enters. Okay. Of course, if I just store it store the vertices, right? I can always make this one into order V, no issues. I can also make this one into maybe order 1. Maybe I store this one as order. I can keep it as a heap, right? If I keep it as a heap, then I can get this one in order log n times, right? I can maintain it as a heap. I can order this one in order log n times, and then this one, how much time does it take for updating? So every time I can update also in a heap in order log n times. So this becomes, so basically, so if the data structure is, say, an array, just a simple array, then time complexity is order V square plus E, right? If the data structure is an heap, the heap, then what happens? Then time for finding a minimum in a heap is log n, right? And but time for updating is also log n. So this becomes order V log V plus E log V. Okay, see, this is, you can think of it, this one as, has improved from here, right? This is improvement from here. Why? Because what happens if the, yeah, someone did ask something?
Yeah, sir, I was asking, like, for searching, for finding minimum from heap is log V, but for making the heap, it will again be order V.
Ah, good. See, we don't make a heap, right? So we start with an empty heap, right? So you can think that heap is being made by updating, right? I mean, initially you can start with that. We have started with a completely a simple heap, okay? But the S has weight 0, everything has weight infinity, right?
Yes, sir.
So then nothing is there. I mean, completely trivial heap. So you don't even need to spend. You can order V to making that heap, right? Now, once you are done with that heap, you took in the minimum. The minimum is S. S comes in, and you update the elements that are there that has to be updated, right? And then you update them one after another. Right. So the kind of the heap is being made on the fly. Is it clear?
Yes, sir.
Okay. Okay. So I'm, by the way, I'm assuming that you guys are familiar with the concept of heaps, right? Anybody here who would like me to go over the heap structure a bit or something? Okay, no, good. So see, these two bounds, I mean, you can say that which is better. That's a very good question. In fact, if the size of E is order V square, then this is worse than this. But if size of V square, if the size of E is much smaller than V square, then this is better than this. So these are trade-offs, right? You don't know from what is required and what is required and all those things. But this is something. So these are the two things that we have. Now, question is that can we do something better? Okay, and this is where data structures comes in. Okay, is it possible to store the data in such a way that I can say find the minimum in log n times and update using constant amount of time? Okay, and this is where the interesting things come in. Okay, so this is where maybe our today's thing is that if the data structure is a Fibonacci heap, so then you can do it in order. You can do finding a minimum in log n time and updating in constant time. Okay, so V times log V plus E, and this is better than this for certain, right? And in fact, this is possibly better than this also for always. And this is where we kind of what the Fibonacci heap does. Okay, so the whole thing changes to how can we design a data structure that helps us to do this thing. Find the minimum in log n time, but update is constant. Okay, now you can of course ask, why can't we be greedy and say that, okay, why can't we find a minimum in constant and update in constant time also? Then we are just V plus E, then a linear time algorithm. Yeah, very good point. So think about it. What happens? Is there any? I mean, this is a very good. If you have this question, then that's the natural question to ask and think about it. Why can or can't we have a data structure where both these two things are constant? Okay. Yeah. Now let me go into. So is it clear what the Fibonacci heap will try to do? Hello.
Yes, sir.
Yeah. So okay. Good. So now let me take a slight detour before I explain you the Fibonacci heap. Okay. So the Fibonacci heap does so when we analyze an algorithm, right? How do we analyze an algorithm? We analyze this algorithm saying that, okay, the worst case runtime is this. Basically saying that, okay, this algorithm at any point of time will take this much amount of time, right? Or in the worst setting, this is the amount of time that will take. But in a data structure, the size of the input is not fixed, right? So in a data structure, what happens is that you have a storage, you have a storage mechanism, and you store using some set of operations, like something like an insert, or you can say addition, or addition of an element to that storage, or remove an element from the storage, or subtraction. Or you can have a small algorithm that says that, okay, I want to, it's what is called this extract mean kind of stuff. I mean, extract mean doesn't have to be there, like special operations you can think of. Like this is a thing that I can press that particular button and the algorithm will just output me the minimum in the thing storage. Okay, maybe you can have extract median. you can have extract, mod, doesn't matter. I mean, something of that form, some special operations are supposed to be done. Maybe there is something called a modify. So there are various algorithms that are there. So a data structure is actually not a single algorithm. It is a collection of algorithms. Okay. And so when I talk about the worst case runtime, what is the runtime of a data structure? And this is not at all obvious. What is the runtime of a data structure? Right. So maybe I can say things like, okay, maybe for every insert, I actually take order n amount of steps. Okay, what does it mean? Okay, not every insert, but if at any point of time I have n elements, I would be needing, I mean, there might be instances where I will have to spend order n time for doing another insert. That is what a worst case thing is. Okay, so maybe I should write it here in a different way. If I say that the insert operation is a worst case operation, is this, what does it mean? It means that there exists a time, there can exist a situation or instance where the number of elements present in my storage is n, and to add one more insert, I will take order n steps. Right? So that is a worst case insert. Fine. Or something similar to say maybe this extract min, right? It can have some order log n to extract it or something like that. But these are in the all of them in the worst case. But when I'm talking about asking, so this data structure has another nice important thing where it differs from algorithms a little bit. A data structure, it is the algorithms or the set of algorithms, right? It is not a one call instance. Are, called multiple times. Okay. So that means that sometimes I can ask insert n different objects one after another. Right? I can ask remove a few times. I can ask extract a few times. I can ask modify a few times. When I am asking, when I'm going to use this data structure in another algorithm, say a Dijkstra's algorithm, I am not interested in whether a particular call, how much time it takes. I am more interested in the total time taken. It might be that most insertions take constant amount of time. But once in a while, an insertion takes a lot of time. In such a way that if I actually do n inserts, one after another, the total amount of time will be order n only. But that's not captured by just the fact that the insertion as a worst case has this much time. Okay, so let me explain you actually one small quick example, okay? So have you heard of this concept of dynamic array? Okay. So the idea is that when you are constructing an array, right? If you ask a C program to write an array, you have to specify what is the length of the array, right? But if you don't even know to begin with how many elements are coming, right? How will you store them? How will you tell? You cannot tell a C program that may give me an infinite array. That is not possible, right? So what is done is that you, at some point of time, you start with some very small numbers. So you say that, okay, give me an array of size 10. Oh, fine, very good. They give you an array of size 10. Some elements are coming and you are inserting. Okay, so there x1, so you have insert x1. You put x1 here. You insert x2, you put x2 over here. And all I'm doing is that I want to store the data. Okay, so I have a string of objects coming. I don't know how many of them, but I also don't want to use too much space, more than what I need to do. Correct. It is something very similar to if I have to store, you have seen in various websites, right? That how many visitors have appeared, right? So you can actually note down all the possible IP addresses from where your web page has been visited. So what will you do is say that, okay, give me an array and I will keep on storing the IP addresses of the people who have come and visited my thing. But problem is that you don't know whether that number will be just 5 of them or 5,000 of them. So if you just ask the computer to produce a 5,000 amount of space for me, then that will be just be wastage of time, right? So, or space. So what you do is that you start with some small amount. So I have just said 10 of them, right? And when the x10th comes, you put it x10. But then when the x11th comes, you say that, oh, okay, see, I have now taken up full space. So give me a bigger array. Give me an array of size 20. And you copy all of them, x1 to x10 over here. And then you put x11 over here. And you throw away this array. You empty the space. So now you have a bigger array. And you keep on doing, right? Then again, after some time, you get x20, and then you have maybe one more element has come, x21. Ah, okay, good. So give me another bigger array. And I give me an array of size 40. And I store x1 to x20. From here, I copy all of them here. And I store x21 over here. And I release this space. So this is called dynamic array storing. Note that at any point of time, I am not using space except for the initial time, which is, forget that, that's a very small amount. I am not using space more than double the amount that I actually need. So it's much less wasteful, right? But what is the runtime of this algorithm? So what is the algorithm clear? How I want to store them?
Yes, sir.
Hello, is it clear for everybody?
Yes.
Okay. Okay. So question is that what is the runtime of the insert operation? What do you think?
If I have to copy them in order of n,
We have to,
if I have to
Copy.
copy,
yeah, you have to copy at some point of time, right? So good. So as you pointed out, this one has a worst case runtime of order n, right? Meaning there, if you just think of it as a one-shot algorithm, right? At some point of time, I might have n elements. The n is the size of the array at that point of time. I might end up spending order n amount of operations. steps, right? But if I ask you a slightly different question, that if I give you m elements, the m elements are coming, how much time will it take? I understand some of the insert operations might take a lot of time. At the same time, some of the insert operations will take just one slot, right? So on an average function, you can think of, although this is not an average thing, right? How much time will it take? Hmm? Any idea? Okay, so let's try to calculate it in slightly different way. Okay, and then you'll see this thing weirdly, beautifully coming out. Let's say that I have m objects, right? Every time I am putting an object over here, I am going to charge them a money. So they have to buy a ticket to call the insert operation. Okay, so let's say, to just for the heck of it, let's say that I will charge them 4 rupees, 4 unit every time. So x1 comes with 4 unit, I put it there. Okay, x10 comes with 4 unit, I put it there, right? Consider that time. Okay, yeah. Or maybe let's start with here. Okay, so beginning. Okay, let's start with this thing. So x1 comes, I have charged them 4 rupees. I have x10 comes, I have charged them 4 rupees. So at this point of time, I have how much time? How much money? I have some 4 into 10 rupees with me. How much money I have spent? Okay, so let's say that every minute or every operation is the 1 rupee cost. So for every element, I have taken one amount, 1 rupee to insert it, right? I've charged you 4 rupees, but I have only used 1 rupee. So I have just used 1 rupees for this thing. Okay, to putting it x1, I need 1 rupee. Putting it in x2, I need 1 rupee. Putting it in x10, I need 1 rupee. So I have got 3 into 10 rupees left at this point, right? Now, when the x11th comes, I am again going to charge it 4 rupees only. I have to be fair. But now I have a lot more operations to be done. So how much amount of time that is taken? I have to create a new big array and copy them, right? Each copy takes 1 rupee. So I am now going to spend how much time? How much rupees? I am going to spend 1 rupee for each of them. Correct. And actually, I don't even need say 4 rupees. In fact, I think I can live with 2 rupees only. Let's see. Yeah. So let's leave it just 2 rupees. Okay. I just ask everybody 2 rupees. Okay. Although I will need 1 rupee to insert each of them. But when it comes down to the end, I have left with 1 into 10 rupee. I still have 1 in 10 from each of the one from each of them. I make a bigger one and I copy it for here. Oh, actually, I need 3 rupees. Sorry, I need 3 rupees. Yeah. Forget, not 2. I need 3 rupees. Okay, good. So I can use that leftover money to copy them here. Now what happens? Say x11 comes, I have charged it how much? 3 rupees. So 1 rupee has been spent for inserting here. Now I am left with 2 rupees. When x20 comes, at that time, I have 2 rupees from every one of these things remaining. Right? I have 2 rupees from every one of them remaining. So at this point, what do? When the X21 comes, I'm saying, okay, I'll make a bigger one and I copy all of them. I have to pay money to copy, right? How much money I have to spend? I have to spend 1 for every one of them. So 1 for everything. So 1 into 20 I have to spend. I already have 2 from everything here left over. So I can pay using the money that I've saved from these people. I can pay to shift all of them here. Okay. Now next one happens. At this point, you can think of this set of X1 to X20 has completely been erased. So they have given some money, whatever money that they had spent has taken care of, done. Now X21, everyone is giving 3 rupees. 1 rupee for going into it. And I will continue till how much? Again, X40, right? At that time, I have amount of money saved from X21 to X40 is 2 per head, right? So 2 into 40, 2 into 20 is 40 rupees. I use that one. So when the X41th element comes, I use that one to shift all of them to the next round. So what is happening? So in some sense, when the first element came, or when the say X12th came, I could have just asked it to pay 1 rupee, but I did not. I asked it to pay 3 rupees. So some of it was my pocket, I pocketed some money. But this money, I ended up saving more and more till a time comes when I need that money to do some more action, from bigger action. Note that I started with possibly 0 money in my pocket, right? Every time I'm asking 3 rupees from everyone. And at no point of time I'm becoming negative, right? So what does it mean? It means that if after m element comes, the total number of operations that I've done must be less than 3m. So that means, although the worst case runtime for any one action, any one call was order n, but a series of m inserts takes order m steps. It is not order m square steps. Is this argument clear to some level?
Sir,
Hello.
how is m different from n here? I thought n is the number.
Okay, so what is n? So n is basically the insert is the algorithm, right?
Yes.
Insert is an algorithm. So insert at any point of time, what is the input of it? So the insert has an input which is an array A and an element, right?
Yes.
So when I say the worst case, meaning the insert operation is linear. In the worst case time, it is linear in the size of the array length.
Okay.
Okay. But that would mean that if I make m different insertions, in the worst case, it would have taken m times n or m times m, right? Or m square kind of stuff like that. But it turns out that no, it is not. Okay. So m insert operation will take only order m steps. This is very similar to what happens, say, if you run a hotel, right? You go to the hotel and the hotel charges you for some money, right? That money, a part of it is required for your maintenance of the hotel in that time, to pay for the people who are the cleaning ladies, for ensuring that all your stuffs are fine and all at that time, right? But every year or every 2 years, right, after enough amount of people has come, right, after say after every 1,000 people have stayed at a particular room, you would need to make a proper overall of that room. You need to change the bed sheets completely. I mean, bring in a completely new set of bed sheets, curtains, maybe even change the furniture. Something has to be done. Renovation has to be done. Who pays for it? That's a massive one-time investment that the bank has, that the hotel has to do, right? But that is a lot of money. But that doesn't mean that that is the money that the hotel pays every time, right, for renovation or any such thing. The reason it is happening is that every time a person is coming, they are paying some extra money. That extra money is being accumulated in the bank, which is being spent at that time, right? So this is exactly what is happening here. So this is what is known as the amortized analysis. Amortized analysis. So amortized analysis is basically, I am not interested in what happens in a particular run of that algorithm, but I am interested in m different runs of that algorithm. Maybe one run of the algorithm is costly, but if I look at it a lot of runs as a single in together, then I see that the algorithm is actually not having too bad a runtime. Is it kind of clear? I mean, I think the dynamic algorithm array is a good thing. Think about it a bit. Okay. There are insert operations in the middle, which is taking a lot of time, right? There are some insert operations, the insertion of the X11 or X21 or X41 is taking a lot of time, right? But if you think of M inserts as a whole, the number of operations as a whole is not more than order M. Is this clear a bit?
Yes, sir.
Okay. So, okay, good. So, so for everybody else, it is fine?
Yes, sir.
Yes, sir.
Excellent. So there are couple of ways of analyzing amortized analysis. One of them is just how I define, where you charge amount of money. Okay, and you charge the money to everybody. Okay. The another one is the when there are different kind of operations is what is called a potential function. Okay. And basically the potential function is another way of doing it. I'm not going to explain it in very much details, but in some sense, the potential function is the amount of money that is there in the bank you can think of at any point of time. Okay, so in the same operation that I just did, the amount of money that is there in the bank. There are times when some operations might be more costlier than the other. and then you spend that money. Okay. So in the case of Fibonacci heap, I can explain Fibonacci heap in a very vague way. Okay. So what is Fibonacci heap? So the goal is to do a few operations. Number one, you want to keep inserting insertion. You want to it can insertion. You can modify some of them, and you are allowed to. I mean, for our purpose, we just need modify, and the other one is extract mean. I just want these following things to be done. These three operations. I have a string of say information that are coming. Okay, then x1 to. So they're not added, like there's kind of a set of instructions. Like insert this, okay, modify this, insert this, modify this. A lot of data is being stored, right? And at certain times of time, I say that, oh, now give the minimum. And okay, here is the minimum. Then we again continue with say, okay, now again insert this one, again insert this one, again modify this, again modify that one, insert this one. Again, give me a minimum, and then we'll give you a minimum. Okay? So this is basically how Fibonacci heaps data structure is supposed to work. It's supposed to support these three operations. Okay, and the goal is to do this one in a constant amount of time, modify also in a constant amount of time, and insert in ordered log n amount of time. Okay, where n is basically the number of elements that will be present at that time. Okay, so this is what Fibonacci heaps does. Now, the best way of thinking it of Fibonacci heap is the following. Okay, say you have a storeroom. Okay, and in the storeroom you are you get or you have your bookshelves, right? Okay, so maybe a storeroom instead of storeroom, bookshelves are better. You have a set of bookshelves, and every now and then you are buying a book, right? When somebody gives you a book, you just take that book and keep it somewhere. Now you can do two things. You can either take your time, work on it, and find out the exact place where the book should be there, and so on and so forth, arranged in a very nice alphabetical order or according to various things and done. Or you can just dump the book somewhere in the shelves. Correct? Another book comes, you dump the book somewhere in the shelves. Now, this is fine for some time, right? It keeps on happening. Maybe the first 10 extra books come in, no problem. First 20 extra books come in, also possibly no problem. But when the number of books that has come up that you have got crosses a threshold, your book starts looking ugly, right? Then one fine day, you sit down and decide, oh, okay, now done. I need to fix this bookshelf in a proper way. And you sit down and you arrange your bookshelf in a sorted way, okay? So that when you have to find a book, you can easily find a book. You don't have to spend a lot of time in finding the book, right? But again, then the next book comes in, you put in there, and so on and so forth. Now, what happens here? What is happening here is that if you are inserting books, it can be done very easily, right? You can just insert in, doesn't matter. But when you are finding a book, then you are going to do some more work, right? You're going to work a bit more and then arrange it accordingly. Fibonacci heap does exactly this. When an insertion comes, or when you modify something, you blindly modify it. You blindly insert it. They're very quick actions. Okay. But when you extract the mean, you say that, oh, give me the mean and give that object, remove that mean from that whole set. Then you go into a hyperactive mode and do some lot of work so that things are back to kind of a nice settled way. Okay, and then again you continue with that. And this is exactly what Fibonacci heap does. Now there are certain properties of the Fibonacci heap that are there, and now question is that should I go into the details of the Fibonacci heap here? Okay, and so let me ask you, I mean, I can go into the Fibonacci heap right now and try to explain you all the details of the Fibonacci heap, but that would be possibly not be that exciting. But with this current, with the kind of high level picture that I gave you, both of the amortized analysis and the Fibonacci heap, and the application of Fibonacci heap, how that can help in the Dijkstra's algorithm. Do you guys want to go back and read it for yourself once? What the Fibonacci heap does? Or do you want me to just explain it?
Okay, sir, we'll read.
I think that will be good, because I mean, now that you should realize that there are two things here, that what this Fibonacci heap wants to do. Fibonacci heap is trying to get modify an insertion into order 1 and extract mean into order log m. Okay, that's first thing. And second thing is that it is an amortized analysis. Okay, so it doesn't mean that a modify operation will take only order 1 step, but it is an amortized cost, meaning it's kind of, you of course, I mean, if the size is small, then I mean, if not much insertion has happened before that, then it is no big deal. You can quickly modify it. If some, so similarly, this insertion also, and similarly this extract mean also. Okay, so these are, so the important thing is that they're all of them are done in the amortized cost. But amortized cost is perfectly fine when you consider applications. But this is not expected algorithm or something. It is just saying that the data structure should not never be looked into a one-time algorithm. It is an algorithm that is where this, it's an algorithm which is applied a few times. Okay, it is an algorithm that is applied multiple times. So that is exactly what where you can possibly make do some progress, or you can save some time in the time complexity. Okay, so I think you guys go back and read this one. I hope that this now you will have a better understanding of this whole thing. Okay, amortized analysis is something that, of course, I mean, is a very important part of algorithms, but unfortunately enough, is not something that we can we could not spend time on this one. And also because so amortized analysis was not done in data structures, is it? Course at all? The MTech CS
No,
students did in data structure course, right?
Yeah, we had, but not in name of amortized analysis. I mean, we had done some similar kind of things, but the term was not there. I'm hearing the term for the first time.
Okay, so if you are hearing the term for the first time, then you have possibly not done this one, because there is no other term for this. This is a very standard term. This is a very standard term. It's called amortized analysis or amortized cost. I mean, the amortized is there in that whole thing. Okay, and there are 2 or 3 different ways of doing it. One is called this charging of charging of people, and other one is called the potential functions. Again, I mean, both of them are more or less similar to each other. Okay, so I suggest that you guys go back and try to read it for yourselves. Okay, and if you have any doubts, again, I will be happy to discuss more. But I think instead of me just shouting it out, it's better that if you guys start thinking a little bit on this direction, that in this way. It's fine. Any questions? Any comments? Okay, so if there's no question or no comments, then yeah,
Sir,
go ahead. Yeah.
like this is not regarding this algorithm or anything. Can I ask you about some reference for general proof systems, learning proof systems?
Learning proof system. Yeah, I mean, go ahead. I mean, what do you want to ask?
I mean, like any good book for learning proof systems in particular.
I mean, what do you mean by proof systems? I mean, that's what I'm trying to understand.
There are these iterative protocols for like given a statement using this iterative protocol interactions. Like some prover will try to prove to the verifier, right? This sort of proof
Oh,
systems.
this IP. Okay. See, I mean, if you want to read those things, I mean, the best way is to look into the complexity courses books. Okay. So there is this book by Arora Barak. So Sanjeev Arora and Bose Barak. So they have now this algorithm, this book of complexity theory. And you don't need to know everything of that book. Okay, so they have a chapter on interactive proofs, interactive protocols. Okay. And you can try to look at it from there. Okay, there is also an by Wigderson, but that's a slightly less technical book. It's written in a more of a philosophical way, but so it might be pretty good for you guys also. That also has some nice this interactive proof stuff. But then there is another one. So this, so what I'm telling here is interactive proof systems or interactive protocols for trying to understand the complexity or hardness of a problem. Okay, but then there are also the other side, which is called the communication complexity, and that is also a big thing where you have to design protocols to solve it. That's a big area of research again, and a very important, a very beautiful area of research. Okay, and yeah, I mean, it is something that if you are interested, you can certainly take a look at it. So it's really fascinating, no doubt about that. So if you want to read that, there is a kind of almost a Bible kind of stuff. It's called Nissan and Kuselevich. So basically, basically the book that I just now told about, there is communication, the complexity theory related books. So the two books that I can, by the way, I'm the name of the book I don't know, honestly speaking, but these are the authors' names, and that's what matters here. Okay, and there's a book called Wigderson. These two books are pretty big, nice books where you can get this interactive protocol stuffs. But then there is the other area, which is the communication complexity. Communication complexity, communication algorithms, and all. And there is this book of Nissan and Kuselevich. Yeah, and yeah, so these two are kind of advanced topics in some sense, but they're very fascinating areas. So if you are interested in the interactive stuff, then these are. But then there are another side of it. Then there are these things from the logic world. Okay, now I am not an expert in this direction, so I don't want to really talk much about here. But in the logic world also there are things that comes in the picture a lot. Okay. And there is, but yeah, this so who asked this question? Can you just say your name, because I'm not unable to see your
Shiva.
Shiva, right?
Kumar.
So you are
Yeah.
from CRS, right?
Yes, sir.
Yeah. So in this thing also there is this something called very related to this cryptographic stuffs here in the complexity theory, which is called the zero knowledge proofs.
Yes, sir.
These are also basically proof system kind of stuff like that.
Yes, yes.
Okay, so they are also somewhere there it comes there,
Sir,
but they are in the more from the complexity time stuff.
sir,
Yeah, go ahead.
sir, are you in logic, sir? Are you talking about the descriptive logic, descriptive complexity?
No, there
like
is
that?
logic where they try to formalize things, formalize games and formalize interactions and all those kind of stuff like that.
Yes.
Okay, so just like the automata is a kind of a linear kind of stuff, right? Now, how do you define when do you say that some language or some problem can be solved by a two-player game? And so on and so forth. There is all lots and lots of things are there here. So if you are interested, you should ask maybe someone like Sujata or someone who are the logic persons in this. Yeah.
Yes, sir.
Yeah, so they are nice. These are nice areas, no doubt about that. They're very, very fascinating areas. And if you guys are interested, then yeah. I must say another thing that I mean, if you guys are interested in any of this kind of work and want to do a master's thesis, then don't. I mean, this is not not only for whether if you want to do this kind of stuff, but irrespective of that, your master's thesis is due in next year, right? 2022. And
Yes, sir.
I would suggest that you guys, with whomever you want to work with, please contact them as soon as possible. Okay, and don't wait till January and February. That oh, now I have to do a thesis. If you really want to do something interesting, learn something, it is better to. You don't have to work for 1 year, but you have to. I mean, that keep on learning a little by little, instead of coming in fourth semester and then doing some work. Okay. Yeah, I don't know about, of course, this pandemic is a big problem, and I cannot say a single thing about what's happening in ISI, whether ISI is going to open up and let people come back or not. I have no clue. But I mean, I don't think, yeah, I have no idea. Has they told you anything about in that direction?
No, sir.
Don't know. I know that, I mean, things are becoming a bit normal. Faculties are going a little bit. I went there a couple of times. I think the PhD students have also started coming back a little bit. But in terms of classes and master students, I am not 100% sure what's happening. Yeah. Okay, so any other questions? Okay, so if not, I will end today's class here, and I will say that there will be no class on Thursday. Instead, there will be a tutorial. Okay, Shayantan will take a tutorial. We have already uploaded a few problem sets. Another problem set on reductions will be uploaded. And if you have not understood yet, I'm telling you, reductions are something that I will emphasize quite a lot in the NSEM. because we have spent such a long time also on reduction. Okay, and reduction is something where unless you practice, you will not be able to make any headway in that full direction. Believe me, in the exam. So please try as much as you can. If you want more problems, we will put in more problem sets. And if 27th is the deadline, is the stuff, right? That is nearly 2 weeks from now. Not nearly, there's exactly 2 weeks from now. I mean, if you guys want tutorials or any discussion on any topic related to this course or otherwise, just drop us a mail or send us the information in the classroom and we will try to arrange one. Okay. But again, this is something that you guys are supposed to tell us. Okay. If you guys don't show any interest in taking needing a tutorial, I don't expect more than 2-3 people to come in a tutorial also. 2-3 people is good enough. But you guys should tell us, see, we need some problems, we need some discussions on some problems, problem sets and so on. So please have a tutorial. Else, I think after this Thursday, we are not personally going to work out any extra tutorials. So there will be no tutorial on Saturday or Monday unless you guys tell it. Okay, of course, there is no class on next week, but again, if you guys want, we can have some discussions on the class hours next week also. Okay, so good. So let's.
Sir,
Yeah.
Sir, there is a question from Midsem, sir, which I had also asked in many tutorials, but sir, means every time one or other contradiction pops out, so sir, the algorithm is discarded. So sir, can you please give some hints regarding the question, if possible?
Which question can you just repeat it so that I can just, I don't remember neither the question nor the answers. That question.
Okay, so sir, there
So
was
is it related to the shortest path thing, is it?
Yes, sir. Yes, sir. Sir, DP into DP, the product of DP into DP should be minimized, where capital DP denotes the shortest distance and the small dp denotes the number of hops, minimum number of hops.
Yeah, so okay, and there was a question that to make it write it in linear time, right?
Yes, sir.
Yeah.
I was thinking that can we make the cost is in I mean while popping the elements we can we can have two arrays of two information stored in for the number of hops and number of distance, small d and capital D. And while popping out, we can keep on multiplying and then pop out from the queue.
No, that you can do. So that is kind of the Dijkstra's kind of stuff, right? Yeah. So I think that was the idea to have that kind of stuff only. But Dijkstra's, okay. So if you think of Dijkstra's to be linear, then it is linear. So you can write the algorithm in Dijkstra, write a Dijkstra's kind of algorithm.
But Dijkstra is not linear.
Dijkstra is not linear. Even with Fibonacci heap, it is not exactly linear. I completely agree.
Yes, sir.
It is linear for only for when the number of edges is more than V log V. And yeah. Okay, so I have to look at it. Actually, maybe there might be some mistake here. So this is that might be another thing. I will try to hand over the mid-sem paper to you guys by sometime by next week, so that you can have some idea about the mid-sem stuff also.
And
Yeah, so
sir,
I will-
can you
I will-
please upload or sir, tell the solution if possible?
Yes. So if I get a solution, or if I remember the solution, I will try to upload it. I mean, there is a possibility that it might not be possible actually. Maybe there was a mistake in that thing. I mean, of course, in that case, don't worry about it. You will get the full marks for the question. But so there might be I have to verify. Maybe all you can do is upload extra. Yeah, the thing is that many of the questions were designed by me on that spot. I mean, so maybe I have made a mistake in that during that time. The problems were not copied from somewhere place. And that's why it's very much possible that I made a mistake somewhere. Okay. Any other questions?
No, sir.
Okay, then. So let's stop the class now.
Sir,
Yeah.
Like, we can come up with a recursion stuff to that problem, right? Recursive approach.
You can come up with a recursive approach also. But I mean, yeah, I mean, recursive approach will not give you necessarily the optimum algorithm for certain. I mean, just like the shortest path algorithm, right? The shortest path, if you do a recursive algorithm, it is not efficient. Right. But yeah, I mean, you can do it. I don't know whether there might still be that one recursive approach. I will see. I will look at. I mean, I will look into. If you have done that one, that's perfectly fine. I mean, whatever you have done, that's okay. I will just take a look at it.
Okay, sir.
Yeah. So whenever some question is asked about solving an algorithm or something, remember that there can be 10,000 different ways of writing it or solving it. Okay. And the right algorithm is the right algorithm. Doesn't matter whether that is recursive or that is greedy or that's dynamic. Doesn't matter. Okay. So I mean, like, it's not like if I have a dynamic algorithm in mind and you have given me a greedy algorithm, then you will not get the marks. No, such things is not the right. It's not. That's not going to happen. Yeah. Of course, in some problems, some particular technique are more suitable to design an algorithm than the other, but that will only help in designing a particular kind of algorithm. That doesn't mean that if you write another kind of algorithm, that's not going to work. So here also dynamic recursive algorithm might very well work. I don't know that. Okay. Any other? Okay, so let's stop now, and we'll see you later.